Okay, just think about this. You just paid, I don't know how many thousands of dollars to go to Yale to sit down and listen to Professor Shankar. He comes in the first day of school, and here's what he has to say.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
unfortunately, he's right. He has to say to them, you tell me what I tell you to say, and then I'll give you a passing grade. Then you can go get a job. Now, if you don't say, even though you don't understand it, doesn't matter whether it's right or wrong. You say what I tell you to say, or you go back to the fields, and you'll be considered an idiot because you can't repeat what I tell you to say, even though nobody knows what it means, and nobody does. Okay, you saw Professor Shankar there at Yale make reference to Richard Feynman, and these are all the Feynman diagrams. He's like me. He looks and sees what's going on, and then he tries to describe it. Now, he can't describe it because there is no way to describe it without using the dipoles. He's showing these photons and electrons smashing together and shooting out bits of this and that, and they can see these kind of things. They have no idea why it's happening. Because first of all, they're working with these giant colliders, so all they can see is these bits and pieces, but they're in trash, literally picking through trash to find these things. And when they see them, they say, wow, look at that, and look at that interaction. Wonder why that happened. Well, we know we started with light. We didn't start with an explosion. We started with light, and we can watch them happen, and I'll show you that right now. Okay, my friends, this is a pretty good video. This lady did, she's a PhD and she's a teacher and so forth. And she realizes that nothing she was told is right. So, this is my model, and it is right. There's nothing that is wrong here. I can show you these particles. I can show you photons. I can show you electrons. I can show you muons and electron neutrinos actually separating. I can show you the tau neutrinos. I can show you fission and fusion, which I will do quite soon. Okay, so this is called the looking glass universe, and she says, I did the double slit experiment at home. And she says, I've done my PhD in quantum stuff and so forth. Here she goes.
So I've done my PhD in quantum stuff, and I thought I understood the theory of this experiment really well. And so my plan was just to explain it to you in a cute little video about how to do the experiment at home. Instead, I got sucked into an odyssey for the last few months where I did all kinds of variations on the experiment, and I ended up questioning pretty much everything I thought I knew about light.
Yeah, you should, because everything they taught you was wrong. All right, I'm just going to run through this very quickly. This is a light wave, and it's caused because there's a particle in there. I'll show you about that particle. And it has a magnetic field around it. So the field has to push everything else that has a field, and everything has a field because everything's made out of these two same particles. I'll show you that in a second. Now, what we did was we sent this through a Venturi, which is this particle is now accelerating, and then it stacks up on itself and squirts through the Venturi, creating Higgs fields. These are Higgs fields. Now, this is the particle. Let me show you in a little more detail, and then we're going to go into some more things about, why we're having a trouble with fusion, because they don't understand the dipole nature of the particle. Okay, CERN has found these particles, CERN and Fermilab. The black one never changes, the white one is glowy and squishy. Here they are right here with our light experiments. The problem they have is they're hitting head on with thousands and thousands, billions literally, of particles, and then they sort through the trash. They found these, They have no idea where they came from. We can show you where they came from, and we can squirt them through a Venturi and actually separate the black from the white. Anytime you separate something, it's called fission. Anytime they come back together, it's called fusion. That's fission, that's fusion. This is the muon, black, heavy-duty particle. This is the white one that is the glowy particle, and it turns into a shower. Precisely. Identical to what CERN, Fermilab, and all the other laboratories are looking for, and we did it. Strictly with light and using a Venturi. You can't see the Venturi because it's so powerful, it's overcoming the actual being able to see it. But it's right there. There's two little round pins that stick straight down, just like that. And the light comes between it. But they're so close together, and they're rounded this way. So the Venturi effect forces, it's called a Warren effect. It forces them to crush their fields right there, just exactly like if they were hitting head on. No difference whatsoever. And the black ones won't let them get out. The black ones keep bashing them through. They squirt out here, and then they come back together here. That's fusion. Fission, fusion. No added energy whatsoever. Accelerating light, I don't see how you can say it's not accelerating. If this was the wave coming normally, that looks like acceleration to me. However, as they stack up, it slows down because they're pushing to shove. Here they're, and then they go bam, 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 whoa, 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 and then they start to push so hard that they separate. Then they come back together right here. I think we get free energy right there. Now I want to tell you something. If we don't do something, we're in so much trouble, it's unbelievable. This is about the White House summit they did on developing a 10-year vision to get fusion working. We should be able to do this just about like that. Let me show you what I'm proposing. And they're spending billions of our dollars to walk around in circles. They don't understand even the particles they're dealing with. Let me show you. Okay, so what we're looking at here is green photons from a green laser. They're coming this way, and this one is the tau, and then they start to stack up, and then they show as the four-banger. Two blacks and a white is a very heavy tau neutrino. Then the photons show up, and then they split up. Now let me show you the red. It's identical. See, this is the green coming through. It's stepped off a little bit, so all the black particles are going this way. No black particles whatsoever going this way. This is coming right at us through the Venturi. So yeah, I believe this one here, there's two pins. There's two pins right next to each other. I believe this one here is a little closer to us than that one. So it's banging off this one and shooting out that way, the dark particles. So they'll go. Now, when we did the red ones, they never came through. They had to go all the way, come around completely. Green is a little harder to work with, a lot more powerful. You see how much stronger the green is? Look, it comes through and just pushes the red out of the way. There's two pins, one here and one on the other side of this. They're coming through, and the green and the red at the same time, and the green just pushes the red out of the way and reconcusses way out here. That's how much more powerful the green is. Same particle. Same particle. Okay, what I want you to do is focus in on these particles here, and then these two, and then here is at the Venturi. So this is the Venturi. Here we know we have the black and the white separate. Here we see a photon. Two blacks, two whites together. Two biomagnets. Here we see what's called a tau neutrino. Two blacks and a white. It's a heavy neutrino. However, as it comes in, it stacks up against these, and they start to push. They're like bouncing back and forth against each other. And when they hit here, the blacks just keep pushing hard, and the whites have to squirt through the Venturi, so they separate. So this is the full progression. On the other side of the Venturi, they come back together, and I can show you that happening as well. So don't forget, you just saw the green, you see the red, you see the tau, you see the photon, you see the actual separation of the two particles at the Venturi, which creates the muon. It's a black one all by itself, and the white one turns into a shower and squeezes through the Venturi. All right, so here you are right here. This is the event happening. There's the acceleration. Here's the splitting of the particles, and here's the recombination of them here. They come back together. Once the white is by itself, it's not going to stay that way for very long at all. Almost instantaneously, it comes back together. And here's what it looks like when it comes back together. All right? It squirts through here, shooting at us these fields, coming at us. The white is here, all right, coming towards us. And all these fields are coming at us. That's these fields right here. You see the black is being gobbled up by the white, only at the tips. You see, these are the tips. And this is exactly what they explain it. They say, anyway, you can see it right here. You see these tips? Right there is this right here. In the well behind, they haven't concussed yet. So they have, some of them have, a couple here and there, but not like the tips. All the tips have turned black, like the white is grabbing onto the black, it looks like to me. That's the way I'm reading this. Now, these are the kind of things I like to talk to somebody about, but I can show the particle has a wave because it's magnetic. So the wave is pushing through all the other magnetic particles because everything is made out of those two particles. And one of those two particles is magnetic, the white one. So they got to push them out. So they heat up a little bit and glow, and this heats up a lot. And then this starts to accelerate and heats up a ton, and the glow, the luminosity is just through the roof. So the increase in energy has to be very substantial, I would say. And if that's true, we should be able to get free energy from this simple Venturi. And this is so compact, you should be able to harvest it, carry it around like a lunchbox, and be able to power a house. Literally, a car. I'm not kidding you, with just a lunchbox size. If this works the way they claim it works, the energy increase should be exponential, absolutely exponential. All right, just remember this, how to calculate electrical power. There's a video about it here, but it says to formulate watts in electric circuits, P is power equals I, which is the number of electrons, it's the current, times E, which is the energy. Well, how do you calculate energy? How do you calculate I? Well, we know that I is the number, physical number of electrons. P is how much energy, power, how much work you can do. P is a work function. E is how much energy potential you have. Is it kinetic? Is it actually doing something? But how much energy do you have? So if we started out with light having a certain number of watts to make that light, all right, see, room temperature molecules, visible light photons, it takes only 3, 4, 5 electron volts to make them happen. When you get into high energy, like alpha rays, gamma, beta particles, nuclear decay particles, you're up to 2 to 10 mega electron volts. But when you get into cosmic ray energies, which is muons, cosmic rays are muons, there's no other way to cut it. You're in the millions to trillions of electron volts. Now, red is going to be in your low energy, but it's going to be a hell of a lot more than down here at you know, a couple of thousand electron volts. We're going to be able to collect some energy off of this. I'm almost certain, because luminosity is energy, and P equals I times E. E is the energy, is the luminosity. The luminosity is right through the roof. All right, what I'm showing you here is an absolutely stunning increase in energetic value if energy is measured by the glow, the luminosity. It's stunning, the increase, and that is how they measure it. Now, think about what you're seeing here. Just take some time to think about it. Do you see this? This is luminosity just on steroids. All of these waves, where'd they come from? What are they doing here? They're in here too. You just can't see them because they don't have enough energy. Now they're being pushed back against. That's why you see them. This one's being sucked forward. That's why you see this one. And that's because it's exactly dead nuts right through the Venturi. If it wasn't, it would be like one of these. You wouldn't even see it. It'd be there somewhere, but it's just not visible. This is pushing back. And this is called reverse electromotive force, reverse EMF. It's pushing back, causing everything to concuss. Look at those reverse waves. Look at those. This is a subatomic nuclear explosion, and it is. I don't care what anybody says. You want to debate me on this? This is a subatomic nuclear explosion. What is a nuclear explosion? It takes the nucleus of atoms, or atoms in general, and just explodes them and breaks them into pieces, and then they become radioactive because they're no longer stable. They want to either attract a whole bunch more of electrons or give some up to become stable. When they do, they throw them off in chunks, and they're damaging. We're using light, so light is not damaging because we're down into those little particles that, you know, as long as you don't put your face, your eyeball right in there, you're going to be all right. It reattaches right here instantaneously. I mean, you might get a few getting past that barrier, but not too many. Most of them are going to get reattached almost instantly. This is a subatomic nuclear explosion. We started with almost nothing. We gained absolutely scads of energy. And we can do this all day long. We don't have to shut it off and make one big bomb and just shut it off, and then another big bomb and shut it off. All day long. All day long. All day long. And we harvest it right there, shoot it down into our receiver, walk around in the woods, take them over to Ukraine, let the people warm up a little bit. You could grow plants, you could do everything with these. Fight fires, disaster areas, no grid required, nothing. Just squirt it right out of there, plug whatever you want in, AC, DC, 220, 120, 50, 60 cycles, AC, DC, MOUSE, whatever you want. Boom. If it doesn't work, you'd know within a couple of weeks. All we got to do is take some of this stuff, engineer that slot just exactly right, different types of materials. So you, once you decide, if you can get extra energy here, and I'm telling you right now, there's no question whatsoever, that is more energy than we started with. That means you should be able to increase it. If you have enough of these happening, you have enough free energy, drive your car, heat your house. Nobody, I mean, we're ruining Earth. Everything, and now even the White House, everybody knows this. All right, this pretty much explains it very simply. Light from a pulsed red laser is coming in here. It consists of photons, and photons have 2 blacks and 2 reds, just like this. That's a photon. Half of the photon is an electron. Nobody's ever known about the dark matter before, which is the muon. The muon here, you see it, muon neutrino attaches to an electron neutrino. That's what they look like in their neutrino phase. When they hit, like in this case, Cherenkov radiation from heavy water, they split. And the muon goes on its way and becomes what's called a sterile muon. And the electron neutrino, with the glowy little pushy burny part, turns into showers. This just keeps just going. Boom. That is gravity. That's dark matter. It's dark energy. And it weighs a lot. Compared to this, it weighs almost everything. So it's like the carrier for the burner. And I'll show you that in an atomic bomb blast. Now what we have happening here was the pulsed red laser. These particles, well, it's actually this particle right here. Boom, 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 boom. Well, the black ones can't get through. The white ones can get big and little. And I'll show you this. And that's exactly what Fermi and CERN say. So the black can't get through. The white squirts through here, 100% white. And then the black reattaches out here. I'm going to show you this actually develop. But this is the entire new electron flood theory is right here. This is Rogers' atomic dipole theory, which is electron flood theory. 100% of anything. If you could present me with anything that they can't understand because of not understanding quantum, and you're never going to understand it. Feynman says it, nobody understands it. You can't understand it because you have to have dipoles. They had just one big positive core in the center and little tiny negatives out here, and it just never worked. It never could work. And you can't get the kind of chemistry that they have and the kind of density of particles with all these just huge particles. They're talking about now putting 1 trillion transistors on one square millimeter. I mean, you can't believe, you know, there's just no way in the world you can use these huge, huge, huge particles. They don't add like this. They come together like this. There's, for every proton right now, there's 1,832 or 33, some 30, I think 33. 1,833 particles make up a proton. Neutrons are 1,834. It's just an even number. And the reason a proton is an uneven number is because it's an attractor. It wants one more to become a neutron. But everything there is made of these two. And every one of these particles is a dipole. It's one of these right here. It has a positive and a negative. And the black part is dark matter, dark energy, gravity, it's everything. It'll sit right on top of its another one. No problem. The white, get away from me. You see it? The whites say, get the hell away. Look at the black ones, they're just laying right on top of each other. They couldn't care less. The black ones, no problem. The white ones, get away, you get away from me. That's what sets up these interference patterns. That's the pushers and the shoves away. Get away from me, you get away from me, you get away. And they just go out in these lines. So she's right. Everything she learned was wrong. Okay, this is where I get to brag. This is what I did right after I got out of the Army. 1970, this goes back to, where I studied, I wanted to go into physics, nuclear physics. I studied every little bit of this, as deep as anybody on the planet at that particular time. And what I came up was everything was dipoles. Everything was dipoles. Dipole, dipole, dipole. You can't get away from dipoles. There is no such thing as a big, gigantic positive core. And also I came up with the fact that the transfer of energy is from light, actual particles of light, as atomic vapor. They're atomic vapor, and they just spray all over the universe. They spray onto plants, and the plants grow. They spray everywhere, and they're heat. All right, there's only two types of energy, basically. There's dipole to dipole interactions. Some of them are polar, and some of them are non-polar molecules. But let me show you the kind of stuff they want you to do. And they think it has some meaning. Just like the guy at Yale says, there's no meaning to this stuff. It's just nonsense, absolute nonsense. All right, I'm just going to tell you, I did all the chemistry, I did all the physics, the light, photons, periodic table, chemistry, all the different principles and rules and energy and configurations. And then you get into all this nonsense, these absolute crazy things. They want you to, look at this. I look at this now, I feel like throwing up. I mean, this was just insane. It was absolutely insanity. They had no idea what they were doing, none. And then they're telling you, if you don't do all this stuff, we're going to fail you. You know, look at this. I can't believe I did all this crap. Anyway, and that was just the start. And then the guy was saying I didn't understand because I kept saying, no, it's got to be dipoles. Oh, you just don't understand. I said, yeah, I don't. Nobody understands, and you don't understand either. And he did eventually admit he didn't understand. Nobody does.